Hello everyone. Uh, in this video lectures, we are going to um, talk about common emitter amplifiers. The word common means um, the emitter terminal of a transistor is to be shared between input and output. Uh, say for instance, um, if you have a transistor, right? One of the solutions is you can have input like this. Yeah, you can have the emitter connected in this way. In this case, the output will be tapped in here. And the input can be fed through something into the base. But there are many ways to do it. One of the ways, the simplest way, is to connect a small signal V in series with a battery. So in this case, as I told you before, VBE is normally 0.7 volts per silicon. For silicons. And it is normally 0.3 for germanium. So what about this case? In order to make this circuit work, VBE knob should be around this figure. If you use some other value, say 1 volt or whatever, the circuit will not work properly. Normally, at least you have to satisfy this criteria. Now, in this case, the collector current can be calculated using this formula here. I've already explained to you in the last few lectures. In this case, VBE, which is this voltage, is the sum of these two voltages. VBE, which is the voltage measured between the base and the emitter here, is equal to these two values, the sum of these two values. And normally, the value of V in is much less than VBE now. So we call this one small signal. And this one is the bias. Bias, biasing voltage. So if we substitute VBE directly into equation 1, we will get IC equals to and then VBE is this one. And remember, in the bracket terms, this term here is substantially larger than 1. So we can approximate this equation by excluding -1 here. And you can simplify the circuit. You can simplify the equation here. And do not forget that V in is always an extremely small value. And this term here is equal to IC naught. It means the collected current in the absence of any signal. So we can further simplify this. And remember, this term is equal to 1 plus V in divided by VT. Sorry, approximate. So if we further simplify this, it will be the IC naught and then IC naught divided by VT, V in. So in this case, you know, IC after a series of analysis, we end up with an expression for IC. And this expression tells us IC is the combination of two values. One is IC naught, and another one is a scaling factor times V in. And this scaling factor is called transconductance. And normally we use GM to represent it. So this is the simplest version. Simplest version of common emitter amplifier. And in this case, IC is equal to IC naught, which is the biasing current without any signal, plus GM times V in. So you may ask, how do we get IC? IC naught. One way you can do it is through here. Right? You can calculate the base current here. So IB times beta equal to IC. Normally, in these situations, IC is given without any numerical of IC. You have to guess the value, and we don't have enough information to calculate IC in this case. The only possibility, uh, um, the only possibility is if we connect a resistor here, then you will be able to calculate IP. Otherwise, uh, IC has to be given. Okay, I will give you 1 minute, and then we are going to step into another case, another version of common emitter amplifier. Okay, now uh, let's erase it now. Um, Another version is, um, you know what, you don't have to bias the base network in this manner. I have told you before, if you do that, then VBE not this battery has to be chosen in such a way that you won't end up with any nasty thing in here. So in this case, VBE not has to be equal to 0.7 volts, otherwise the circuit won't work. Another solution is to do this. So you have IB calculators properly. Uh, Based on by using Kirchhoff's voltage law, you can calculate IB. So in this case, VBE naught um, plus V in plus and the potential difference in here is equal to 0.7. So in this case, IB is equal to VBE naught plus V in, sorry, minus this is not a good idea. And then RB, and V in is normally an extremely small value. too small to be considered in this calculation. So IB so this is one solution. And remember, the V in doesn't have to be connected in this way. This way is not safe. You can do this. V in. So this is another way. Now, all these versions have their own limitation. In this case, you need two batteries to implement this circuit. VCC is one, another battery is here, VBE not. So this is a very cumbersome situation. So what we can do is to do some other technique to bypass it. So instead of using two batteries, this one and this one, we use only one battery. So what can we do? We can retain VCC. VCC is still powered by one battery, but this one, there are many ways to do this. One way is we don't do anything. So we can use the technique so-called fixed base. So case, sorry, version 2. Okay, this one is version 2. One way we can do it is do it here. So we also need to go through the similar steps in order to find out the amplification factors, the voltage gain. The good thing about this circuit is there is no DC voltage here. And in this case, the DC voltage is to be determined by the DC voltage of the base will be determined by VBE here. So based on this level, first of all, we have to determine the biasing condition. So biasing condition let's take a look in this loop here. You know the voltage here is always 0.7 volts. And to determine the DC biasing, the capacitor is considered as open circuit. Open circuit. And now there is no current here. The only current is available is IB. So based on the by using Kirchhoff's voltage law, we have VBE equals to IB times RB. Now we have to put a minus here. So if you know IB, actually we don't need to use the minus sign. And if you know IB, then you will know IC. And the current here is, yeah, let's take a look in here first. As long as we know IC, then the next thing can be determined automatically. And this IC is actually equal to IC naught. Because there isn't any small signal here. Vin is absent here. We have already treated the circuit here open circuit. And the output is also open circuit. Now, I told you before, the next step is to use the small signal analysis. To analyze this circuit. Now, in this case, the first thing that you need is to replace each of the transistor with this small signal equipment. So in this case, you can replace it with R pi. And then and I have already told you in the last lectures, GME pi. And you can connect the circuit in the same way. And we short circuit all the capacitor. First, short circuit all the capacitor, all the capacitors. So we short circuit it and short circuit it. And all the DC voltage, all the independent DC voltages are considered as AC ground. All the independent voltage source voltages are treated as AC ground. So in this circuit, you have one independent voltage here, VCC, So this one is to be connected as this ground, and this ground is so-called AC ground. The only big difference between this ground and this ground here is um, the connectivity. So the voltage here, the AC voltage here is zero. The AC voltage here is also zero. But in DC, right, this is uh, this terminal here has voltage VCC. So in small signal analysis, you can just ground this. And in small signal analysis, this ground is not very much different from this ground. So you can actually redraw this circuit. You can move this RC here. This ground can be moved to here. And you can use this circuit to calculate you can use this circuit to calculate the voltage gain. And first of all, the V pi is the voltage across this resistor. And according to here, V pi is equal to V in. So V in is equal to V pi. And if you look at the circuit here, and if you use Kirchhoff's voltage law to calculate the voltage, the sum of the voltages around this loop, then we will be able to find the voltage gain. So here, minus V out divided by RC. And then the current here, GM V pi. And E pi, according to this equation here, is equal to V in. And we are arranging the equation. Yeah, V in move to the other place, and we end up with RC. And V out over V in is normally called voltage gain. And what is GM? GM, by definition, is the transconductance. The way how to calculate it is IC naught divided by VT, like what I have shown to you in the previous example. So this is the version 2 of the circuit. You only need to use one battery to power the collector, and the rest of the circuit will be taken care of. And based on the analysis here, we have this voltage gain. And IC naught is equal to this value here. You may just rewrite this and VT and then RP. And VBE, as always, for silicon has to be 0.7. So this one is 0.7. And VT is 0.026. So this is version 2 of the circuit. Okay. How now? This is one way. Another way we can do it is to bias the base. You can still keep the collector circuit. We out. So version 3. This is so-called fixed base biasing. This is called fixed base biasing. And the input can be fit through here. So this is version 3. Again, we are going to go through the similar analysis, DC biasing. This is so-called DC. Yeah. Anyway, you can try this. First of all, DC biasing. In DC, all the capacitors are considered open circuit. So we forget about input output voltage, and the voltage at in here is VPE, which is 0.7 volts. And we can deal with the calculation step like this. First, IP, the DC current. There is a small amount of DC current going into the base terminal of the transistor. And we have to assume that the beta, the variable beta, is zero. So in this case, if we consider if we use the Kirchhoff's voltage law to calculate this law, if we end up with the equation VCC is equals to IPRB and then plus 0.7 volts. And based on rearranging this equation, we end up with VCC minus 0.7 divided by RB. And remember, IC is equal to beta IP. So we can rewrite this equation in this manner. And now the next thing that we are going to do is to do small signal analysis. So we are going to erase the all information. The very first thing that you need in this case is to sort all the capacitors. Sort all the capacitors. So we sort it, and replace each of the transistor with its small signal equivalence. Replace each BJT with its small signal equivalent. So in this case, we replace this one with small signal. You can use pi model. V pi. Too small. And the current source here is GM V pi. And I have told you VCC is a fixed DC voltage. It is a AC ground. So we can do it in this way. And this ground makes no difference with the physical ground here. So in other words, we can move the resistor down here, and this ground move to here. So this one done. And again, we can do the same for the circuit here. So the circuit is a lot simpler, and our job is to determine the voltage gain. So the next step is to replace each independent voltage source, independent fixed voltage, with AC ground. So now, how are we going to calculate the amplification factor? One way you can do it is to make use of the network here. We know that V in is exactly equal to V pi. And by looking into the network, IC is equal to minus VO divided by RC, and it is also equal to GM times V pi. And if this is the case, we can just say, yeah, we can just erase this part. GM V in. So by moving the circuit here, moving the variable here, rearranging the equation, we end up with minus GMRC. And this is so-called the voltage gain. And GM is IC naught divided by VT. And IC naught is equal to beta VCC minus 0.7 divided by RP. So all the rest is downhill. So this is the case based on the information from this circuit. And by substituting this equation, IC naught will be this bracket expression, and we end up with the voltage gain here. Okay, this is version 3. And how about version 4? Version 2 and version 3 are based on the network, the so-called fixed biasing. But now we are going to step into another technique. This is so-called voltage divider technique. So I will give you about 1 minute and then you diverge the material here. This equation came from the DC biasing box. Okay, let's try the fourth version, another version. VCC. And then let's copy the collector network. And again, the output is to be tapped here through a capacitor. And beta will be given. And previously, we have tried to bias the network. But now, what if we want the voltage to be floating? So we can have this way. And in this case, R1 and R2 can be chosen. Can be chosen to be a more practical values. So R1 and R2 can be smaller in values, can be small in values. The first thing that we need is to calculate IC. And we can do that through the so-called DC biasing step. So first thing, right, is to calculate IC. In order to calculate IC, you can calculate IB. But how can we calculate IB? Again, we can, DC biasing. We can open circuit first. Open circuit all the capacitors. So we open circuit it, and we open circuit this one is here. So basically, here is handgun. So the next step is to redraw the circuit, yeah? R1, and then there's a voltage source here, and this is the DC voltage, VCC. So we don't need this part. So we treat this circuit as we just assume that we have two independent DC voltage supplies. We have VCC supplying the collector network, and we have VCC the same value to supply the base network. So based on the circuit here, we can also use the so-called Loften analysis. Remember, the series combination of VCC and R1 here can be converted into Loften source. So that one is to convert it into Loften source. So this one here is equal to VCC divided by R1. And the rest of the circuit can be just copied. RB, sorry, R2 this, R1 and R2. And you have two resistors connected in parallel. Then what we can do is to merge them together. And we end up with a single resistor, R1 in parallel with R2. And now we can just further simplify this circuit by converting this part into Thevenin equivalence. So this one multiplied by this one, VCC or R1, R2. And we have a voltage source, and this all these are DC value. And the resistance is here. R1, R2. Now, the base emitter voltage should be around 0.7 volts. And we can use Kirchhoff's voltage law to calculate the value of IB. Yeah, we can apply voltage, Kirchhoff's voltage law in this loop here, and we calculate IB. So let's do it. So yeah, I think it's okay. So the voltage source here, VCC, and then R1, R2, R1 is equal to IB and then plus 0.7. And based on the information given here, we end up with this equation. And we can use this equation to solve, to calculate IB. IB, IB, right? This is the DC value. Minus 0.7 divided by so this is the way how we calculate the IB. The next step is to use the relations. IC equals to beta times IB to calculate IC. So based on the information given here, we can just say VCC to write this into another line. Too crowded. Let's do this. Now, the value of IC has been calculated. And with this in mind, you can simply calculate the voltage gain directly. And again, we can do this. We can just rewrite the circuit. And we are going to use IC to do the small signal analysis. Small signal analysis. And the circuit is here. VCC. And for the time being, right, let's keep this value. IC has been calculated through this equation. So you divide it by this value, then it will be much easier. Okay. Now you have this simple circuit here, and as I told you, the very first thing that you need to do is to plot all the capacitors. You saw this, and replace each BJT with its small signal equivalent. Replace all BJT with their small signal model. So this one here, we replace it. And now the next step is to replace all the independent voltage source with their AC ground. So replace each of the independent voltages with an AC ground. So this means this VCC is just a ground. And this AC ground is not very much different from the physical ground here in AC. So we can redraw the circuit. And stand here. And as before, we can just use the same way to calculate the voltage gain. We use Kirchhoff's voltage law to this loop here. At this point, we just calculate the current. IC. IC is equals to, according to here, is minus VL divided by RC. And is equal to V in times V pi. And what is V pi? V pi is the voltage across this resistor. And the voltage across this resistor is V in. So from here, we know that IC, this one here is GM V in. And we can rearrange the equation in a way to calculate the voltage gain. And what is GM? GM is IC naught, or IC, it doesn't matter. It's RC. And this IC is here. So I think it's pretty clear now. You just substitute this IC into here. Then the voltage gain will be done. If you have any question, please leave the questions in the comment sections or communicate with me by email or in the class. I will try to help you. And okay, thank you.